Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week, despite the fact that it is Thursday. We usually have at least 2 in the can by now. But today I showed a map on the daily weather update which showed a forecast 24-hour temperature change, but it really wasn't the surface temperature change. And what I did today, I started thinking about this and I thought, let's say that Dallas, there's a complex of thunderstorms over Dallas at 3 o'clock in the afternoon, and it drops their temperature from 95 to 70, okay? So when I showed that 24-hour temperature change map in the daily weather update, the next day, if Dallas doesn't have a bunch of thunderstorms over them, it will show a huge temperature increase, and it may be tempting for you to think, oh, they had a big warm front go through the area or something like that, when there was really no air mass change at all. It was simply the fact that it was pouring rain at the time that I was showing this 24-hour temperature change. So by taking a look at the average temperature over the lowest mile of the atmosphere, I think it shows or does a better job of showing you where the major weather systems are and how the overall temperature pattern is changing from one day to the next. So that's the reasoning behind all of this. So let me go ahead here. And there's just going to be a little bit of math in this, so bear with me. So we've talked about this concept of thickness and temperature before, where if you have two surfaces of constant pressure, the distance between those two surfaces is proportional to the temperature of the air between those two surfaces, okay? So let's say that the equator is off to the left here and the North Pole is off to the right. And we're going to have a constant pressure surface of 1,000 millibars, which for the sake of simplicity, we're just going to say that it's fairly level. And then the constant pressure surface, easier for me to say, of 850 millibars is going to be above that. That's usually about a mile above the ground, at least when you're near sea level. And so because it is warm at the equator and cold at the North Pole, you would expect a distance between these two surfaces of constant pressure to be larger at the equator than it would be at the pole. And indeed, that is the case. So by taking a look at the distance between this pressure surface and this pressure surface, we can calculate what the average temperature of the layer between those two is going to be. So let's get into just a little bit of math here. Now, in the past, I have actually gone through the derivation to get to this equation. I'm not going to do that today. But basically, what this equation says is that the natural log of pressure surface 1 to pressure surface 2, and in this case, it's going to be 1,000 millibars P1, and P2 is going to be 850 millibars, is equal to the gravitational constant, which is the rate at which objects accelerate as they fall toward the Earth due to gravity. That's 9.8 meters per second squared. The gas constant, which is R, is 287.05. And the temperature in this case, I'm just going to arbitrarily say it's freezing. But the units have to be in Kelvin, okay? So it's 273.15 degrees Kelvin is the freezing level. And if you take that times the thickness, or the distance between those two pressure surfaces, then that equation all works out. So the natural log of 1,000 over 850 is 0.16251893, okay? If you multiply 287.05 times 273.15 and take that number and divide it into 9.8, you get 0.000124999 times the thickness. If you divide both sides of the equation by 0.000124999, the thickness ends up being 1,300.27925 meters. And we generally round that off. And 1,300 meters is a good estimate as to where the boundary is going to be between liquid precipitation and frozen precipitation. Okay, there are some minor exceptions to that, but in general, that's a good starting point. Now, instead of the temperature being freezing, let's up it 1 degree Kelvin, okay? So now, the only thing that's changed here is instead of having 273.15 in the denominator, we've got 274.15. So when you do that calculation, the thickness turns out to be 1,305.03957. So it's 1 degree warmer, and the thickness is larger, 1,305 versus 1,300. Okay, you with me so far? Okay, so if you subtract those two numbers, you get 4.76 meters. So that means that if you increase the thickness by 4.76 meters, that's going to correspond to an increase of 1 degree Kelvin, which is also the same amount or the same temperature increase as 1 degree Celsius. But we deal with Fahrenheit here in the United States, don't we? Okay? And a Fahrenheit degree is 5/9 the size of a Celsius degree. So if we multiply 5/9 times 4.76, we get 2.64 meters per degree Fahrenheit, okay? And so if the thickness changes by 2.64 meters, increases by that amount, the average temperature of that layer is 1 degree Fahrenheit warmer. If it's 2.64 meters lower, then it's 1 degree Fahrenheit colder. So I decided that I would contour every 2 degrees Fahrenheit, which would be twice 2.64 meters, which turns out to be 5.28. And so that is what led to this map here, okay? So I simply calculated the forecast difference in thickness from 5 o'clock today to 5 o'clock tomorrow and contoured it so that it corresponded to every 5.28 meters, which would be about every 2 degrees Fahrenheit. And so the shadings here, the first shade would be where that shade starts would be 2 degrees, and then you get to the second shade and that's 4, and the third shade is 6, and so forth. The legend here actually corresponds to the actual thickness, okay? But what I did was, you know, correspond or translate that thickness value to a temperature value. And so that's what you see in here. And it makes more sense because, you know, there's an area of high pressure up in here. The clockwise flow around that is driving a cold front southward, and so you're getting cooling behind it here and warming ahead of it and so forth. So I just thought that it represented the overall pattern better and gets rid of these anomalies that can be created by thunderstorms occurring at the wrong time when I am trying to show, you know, the 24-hour temperature change and trying to show how that relates to the overall large-scale pattern. So I hope that makes a little bit of sense. That was sort of fun for me to write a little mini computer program this morning to do that. There are the credits. That is the bonus weather video #1 for this week. Another one will be coming up tomorrow. We'll just have 2 this week. And the next daily weather update coming up tomorrow as well. So hope that didn't drive you too crazy. Hope you have a wonderful Thursday evening, and we will talk to you again tomorrow. Take care, everybody.